All right, so let's jump over to our equation writing homework. So look at your equation writing homework. We're going to modify those equations just a little bit by checking ourselves and then also balancing equations. So we're going to take maybe about 20 minutes worth of notes first. So have your equation writing homework out first, and then we're going to go into note mode. I've got a couple really cool demos for you guys today. I think you'll be excited to see those. Okay, so I want you to talk in groups first. We don't need to write this down necessarily. Talk in groups first about these couple of questions here. Go. I hear you discussing.
Oh yeah. They're not lost in the area.
Yeah, like evidence for chemical change. All right, 3, 2, 1. Give me layman's terms. What is the law of conservation of mass or matter? Jacob's table.
No matter can be lost or gained if it wasn't there in the first place.
Okay, so it's not going to be lost or gained or created or destroyed. I'm going to modify that to speak to how we're talking with reactions today. Matter, aka atoms, right? Because atoms are a form of matter, are simply rearranged. Right, so as we take reactants and we react them and we form products, we're just rearranging atoms into new forms. Boom, we've made new things, but without any kind of destruction or creation. We're just rearranging to make new compounds. Chemical changes, CJ's table, give me one. So combustion is going to show us the formation of something, because combustion is a type of reaction, which would be obviously like a chemical reaction. So give me what you see with combustion. Okay, I'll say heat. What else did you say, Hannah?
Gas.
Gas evolution. You guys have any others? Precipitate formation. Elizabeth's table.
We have oxidation.
So oxidation is a type of chemical reaction. That would be hard to explain as like a observable change. Give me something else.
Color change.
Color change could be a new compound that has a different color, right? So we can see that ST's table. I took all the good ones. You guys have anything else? Hannah?
Rust.
Rust is going to be a specific type of chemical change. So all of these are just like observations we make within the chemical changes. Rust is like iron oxidizing, so it's kind of combined there. So heat being produced, sometimes what comes with heat? Fire, right? Seeing flames and fire. That's an easy observation that would indicate chemical changes. That's a pretty good list, okay? So diatomic, give me the 7 diatomics. Give me one from each table. Maverick's table. I need a diatomic molecule. O2, next. Cole's table. F2, next.
O2.
It's right here.
N2.
N2, next.
CL2.
Cl2, next.
BR2.
Br2, back table. I2, front table. H2. So we call those on the periodic table the big 7 in hydrogen, because it makes a big 7 with reference to starting at nitrogen, O, F, and then down. So that's a big 7 in hydrogen. So when do we write them as diatomic? Literally by themselves. Like I say oxygen gas or hydrogen gas or nitrogen gas, whatever it may be, by themselves, not when they're combined within a compound. And then crisscross charges, when is that applicable? Ionic and acids. And then you shall never do that with anything covalent because they're not ions, right? Okay, so I feel good about that. That's looking good. This is just a brief review of reactions and how we look at an equation and say, okay, where are the reactants and where are the products? Remember, reactants are always on the right, on the left side. This is like back from unit 1. And products are what is produced, or products are what are formed. And again, law of conservation of matter applies. We don't create or destroy, we simply rearrange atoms. Give me a thumbs up if this is all good for you. Does it all make sense so far? All right, so you should not be constructing your foldable anymore. You should be with me. So drop the foldable. Thank you. All right, so the way that we're going to start to indicate to each other that we're not criminals, we are going to be abiding by this law of conservation of matter, we're going to start to balance chemical equations, okay? So this is us following the rules. So you'll hear me say BCE from now on, which means what? Balanced chemical equation. So to balance something, once you have written the entire reactant and product system out, what do you add to indicate that you're balancing it? Coefficients. You do not add subscripts. Subscripts are already there because you've either crisscross charges or you saw a prefix and you added a subscript. So basically, once you've written everything out, don't change it. Just add coefficients to balance. So that's what we're going to do on the 10 equations you guys just wrote, okay? So have that out for me, the equations that we just wrote down as of yesterday. So we already checked some of these, so I'm going to go through the first couple pretty fast because you already have the equations down. But we need to count atoms. Now, in middle school, you guys balanced a little bit, and you guys probably wrote down all your elements and wrote down, oh, on this side I've got 5, and on this side I've got 3. Well, how do I make it balance? We're doing this in our head because it's not worth your time to write it out in a line and kind of use more time than you need to. So let's just walk through one at a time, okay? How many zincs do I have here? 1. How many zincs do I have over here? 1. Okay, so there's a little 1 behind the zinc because of this crisscross of charge system, and we've reduced. So far zinc is balanced. How many coppers do I have here? 1. How many coppers do I have over here? 1. Okay, balanced. And then notice that sulfate, this happy family sulfate, did it get detached or did it break up? Did sulfate itself break up? No, because there's sulfate and there's sulfate, right? So instead of breaking it into thinking about sulfurs and oxygens, you can think of it as a happy family sulfate, and that makes your life a little easier. So this sulfate, how many are there? 1, because there's a subscript of 1 behind the sulfate. And how many are here? 1. So what's the coefficient, or so is everything balanced?
Yes.
So what's the coefficient on all these? 1s, right? So we don't want to say 0 because I can't put a 0 in front because it would not be there. So these are all 1, 1, 1, 1. Cool? All right, so let's go down here. Magnesium chlorate. How many magnesii do I have? How many? 1. Don't question yourselves. You're good. 1, because there's a subscript of 1. And how many are here? 1. Okay, so far so good. How many chlorines are here? 2, because the subscript is outside the parentheses, and it gets distributed into each of the elements inside. And that distribution is a multiplication, not an addition. So that's 2 times 1, which is 2. How many chlorines are here? 2. So far so good. Those are checks. Okay. So magnesium and chlorine are balanced. How many oxygens are here? 6. 3 times 2 is 6. Okay. How many do I have here?
2.
Okay, so I shall only add coefficients. So what number has to go here?
3.
A 3. So that 3 is now being distributed to every subscript following it. Now, this is simple because it's just O2 by 3 times 2 is 6. So there are 6 oxygens here and 6 oxygens here. So what's the ratio? Coefficients was 1, 1, 3. Okay, let's keep going a couple more together and then let you guys roll with it. So wait, how many sulfurs do I have on each side? 1. How many oxygens do I have on each side? 2 and 3. Okay, so this is where we apply the rule least common multiple. So we have 2 and we have 3. We can't really get those to be the same without multiplying them both by another number. So what's the least common multiple between 2 and 3? 6. So how do I get them both up to 6?
2.
Multiply by 2 on the one and multiply by 3 on the other, right? So I definitely want to multiply this one by what? 3. And I definitely want to multiply this whole compound. I can't just multiply the oxygen because it's a compound, so I can't selectively apply my coefficient. The coefficient goes in the front and applies all the way through. So if I want to make oxygen 6, what do I need here?
2.
A 2. Well, done, got oxygen fixed, but what did I do to sulfur? So I made 2 sulfurs. So what do I need over here? A 2. So you're just kind of going back and forth in your head, and then you kind of do an overlook at the end, like, yep, 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 I've got everything balanced. And let's do this last one together. So like I said, if it's a polyatomic ion and you can keep it together, if it has been kept together, think of it as one entity so that you're not thinking in separate little elements as it goes. So how many silvers do I have across the board? 1 and 1. Good. So do I want to think of this as nitrogen or think of this as nitrate?
Nitrogen.
Let's keep it together because it's here together as 1 nitrate and it's here together as 1 nitrate. So both nitrates are balanced. How many sodiums do I have? 1 and 1, and bromines? 1 and 1. Naturally, that one is balanced itself already. All right, so can you guys chat in groups and try to balance? I'm going to put the answers up so you can, because of course you couldn't balance if your subscripts are wrong, right? So you need to make sure you're in good shape. So check these 1, 2, 3, and then balance them in your groups.
You have to add 2 to the H2O. That means 72 is 4. So we put the 2 in front of the 8. No, but you have to put the So we have to add 2.
All right, let's make sure these are balanced together first before you get too far ahead. Back to me, 3, 2, 1. Dunn's table. What'd you tell me your thought process for number whatever this is?
Well, first we counted the hydrogen atoms, and then those were even.
Okay.
But the oxygen atoms were not. It was 1 and 2.
Okay.
So we put a 2 in front of the H2O.
And that applies not only to oxygen but to hydrogen, right?
And then we put a 2 in front of the H2.
Good. So once you apply the 2 here to balance the oxygen is fine and dandy, but then that made 4 hydrogens, so you need to make 4 hydrogens there by applying the multiplication rule. Y'all's table, number this one?
It's pretty much the same thing, so we did like something similar. We looked at the mercury and realized that they were the same, but the oxygens weren't, so we put a 2 in front of the first one, and then a 2 in front of the mercury on the second one since it was unbalanced.
Since by changing that, you changed the mercury. Very good. Ryan's table up here on this one. What do we need to do? It's a little bit more complex, right? So tell me about potassiums first.
So they split up.
So tell me about potassiums. Are the K's balanced?
Yeah.
Yes. Okay. So we're not going to touch those. There's 1 K and there's 1 K. Tell me about the iodines.
It's not balanced.
Okay. So I have 1 iodine and 2 iodines. So what do I need to do?
You have to put a 2 in.
So I have to put a 2 here to balance the iodines, right? Well, then you're like, darn it, what did I do?
The K.
Messed up the K's, right? So I have 2 potassiums here. So what do I need to do here?
Put a 2.
Put a 2 in front of the potassium. So now potassium's balanced, iodine's balanced. What's next?
The
PB is what?
But
Okay, so lead is
1.
1 and 1, so they're balanced. Okay? And then what do you want to call this? Okay, and so I'm good with keeping this not N and O's separate, right? Because this is nitrate, and again, I see nitrate over here. So happy families stay together. I'm going to use it as a full entity. So how many nitrates do I have? No. How many? I have 2. That 2 subscript is applying to all of nitrate. So I'm saying overall I have 2 nitrates. So how many nitrates do I have?
2.
How many do I have here?
1. Oh, 2.
2, right? Because this 2 applies across the board to this 1 to make 2 overall nitrates. Okay. Now, if you don't like keeping the polyatomics together in your head, and you're like, I'm better off than as thinking it as separate nitrogen from oxygen, it'll work out the same way. It just takes you a little step longer. Okay. All right. Check yourself here, and then balance. I think these are the last 3. All right, I hope that was enough time to work with this one. I like the first one because it makes you think a little bit more in terms of like how you can change coefficients even if you've already put it down. Saw you guys are racing, which was good. Kendall's table, get me started. You see 1 aluminum, and then what do you see? Okay, so then what do you want to do with that? Okay, so you probably put a 2 here first because you're like, okay, I got to get 2 aluminums. And then I see 2 oxygens, and then I see, and so what do we think of there? Okay, and what's the least common multiple between 2 and 3? 6. So what do I need here? A 3, and what do I need here? A 2, right? So that 2 applies to a 3, check, check, 6 oxygens, but this 2 also applies to the aluminum, so it makes what? 4, so what do I need here? Make it a 4. Okay, so that was the 2 going to 4. I did, you guys will learn those tricks one day. Okay, so next one, let's just go through the line. Magnesium, what do I need? Nothing, it's got a 1 and a 1. Chlorine. Okay, so there's a 2 here, so I see the ammonium chloride. So I have 1 here, so I need to put a 2 coefficient. Okay, but now I've got 2 ammoniums. So what do I see over here? Okay, there's only 1 ammonium currently. So if the parentheses are around, it helps you write the parentheses. So I'm going to put a 2 in the front here. And you're like, oh, darn it, now I've got 2 nitrates. And then you're like, oh, double check. Whew, we're good. It's self-balanced as we did that. So 1, 2, 1, 2. Last one, with this manganese 4 oxide, that is our catalyst. So we do put that, it says in the presence of, but that's a catalyst we're putting on top of the arrow. And then going from there. So I see phosphorus 1 and then 1 phosphorus, hunky-dory, good. 2 oxygens, 5. Okay, I can't make 2 equal 5, so what do I think of here? Least common multiple. What is the least common multiple between 2 and 5? 10. So what do I need here? A 5. And what do I need here? A 2. That's a 2 in front of the phosphorus pentaoxide, okay? And then what do I need over here? A 2, because I've just made 2 phosphori, so I need a 2 here as well. Give me a 1 out of 10. How do you feel about the process of balancing? It's okay if you're not a 10. Because we're going to be practicing this the whole day, so you're okay to get to move on to the next phase. Okay, so you have your foldable back out, okay? On your foldable, here's what I'm expecting of you. Here it is. So if you want to write, I will write this on the board just so you can see the instructions kind of now. But you guys are going to have, okay, so 1, we've constructed it. Check. 2, you're going to be describing each type of reaction. With that, that's going to consist of you labeling the front with the reaction type. Who's already done that? Okay, so we label the front, and then you're going to illustrate with some, either a picture, it can be like an analogy to something in real life, but just a pictorial diagram that would represent that style of reaction. I have some examples and notes, so this is going to be kind of an interactive foldable. We're putting information from it within. The definition of the chemical reaction. Can you guys stop being stupid? Thank you. Definition of the chemical reaction. 3, a general reaction template, which is just I'll be providing that for you as well. So the general reaction template. If you'd like to write this down someplace, because I'm not going to have this on the board the whole time, okay? An example of the chemical reaction. And then color, right? Color that would be exciting to go back and review with before a test. So don't make it boring. And then the chemical reaction, it can be one that I provide for you. It can be one that you find in your problem set, or one that you maybe know about from the real world. So I'm going to show you guys this video first. Okay. So the only two that we're going in detail about today are synthesis and decomposition, and that's because they take a little longer to learn, just because they have a little bit more detail to them. The other ones are actually pretty easy. So let's watch this together first. If you'd like, you can go ahead and write down some of those pieces of information in your foldable.
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 29. It's on synthesis and decomposition reactions. If I were to ask you which of the 2 reactions you see on the left is a decomposition reaction, the tendency is to choose the rusting railroad car. And the reason why is it looks like it's breaking down. But if you think about it, what is rust? Rust is a combination of iron and oxygen, and so this is actually a synthesis reaction. And so if we ever take atoms and molecules and combine them together to make a new compound, then we've got a synthesis reaction. So what's an example of a decomposition? The breakdown of water into oxygen and hydrogen gas is going to be an example of that. And so if we take atoms or molecules and we combine them together to form a new compound, we call that a synthesis reaction. We're making something. Likewise, if we take a compound and break it down into atoms or molecules, we call that a decomposition reaction. Lots of times that'll generate a little bit of heat. And we can use both of these reactions in the chemistry lab to do simple stoichiometry and practice our lab techniques. And so synthesis reaction are when we're taking atoms and molecules and combining them together. So let me give you a couple of examples. Let's say we take magnesium, get it a little bit hot, and then allow it to combine with oxygen. It's going to make magnesium oxide. And so when it's done, you're going to have a new solid that's creating. We're taking a solid and a gas, and we're making a new solid out of it. Another example of a synthesis reaction could be the carbonation of water. And so this is me adding a little bit of carbon dioxide to my soda stream at home, and what's going to happen inside there is that the carbon dioxide is going to combine with the water, and it's going to make carbonic acid. So that carbonic acid is going to lower the pH to around 4, and it's going to change the taste of that carbonated beverage. What's decomposition then? It's when we're taking a compound and breaking it down. So here's an example. If we take sodium azide and break it down into sodium metal and nitrogen gas, that'd be a decomposition reaction. So if we have one reactant and two products, it's a good idea that this is probably a decomposition reaction. Where's an example of this actual reaction? Well, this was used in early airbags. And so what you can do is you can put some sodium azide inside the bag right here. It's totally stable, but if you add a little bit of heat to it, so there's an igniter inside there, it's going to quickly break into sodium and nitrogen gas. And that nitrogen gas is going to fill up the bag really quickly. Now you can imagine a bunch of nitrogen in there is not a good thing. That's highly reactive as well. And so they also put chemicals in here that react with the sodium. Another example could be right here. I'm taking hydrogen peroxide and then I'm simply adding a catalyst to it. I'm adding the enzyme that's found in yeast. And so the yeast isn't part of the chemical reaction, it just serves as a catalyst. And so what I can do is I can add hydrogen peroxide to it, seal it up, and I can give it a little bit of a shake. And what it's going to do is it's going to break down into water, and then it's going to break down into oxygen. And that oxygen is going to fill up the bag. Now, if you feel the bottom of the bag, it's going to get warmer and warmer. And the reason why is that we're releasing energy as we break those bonds and form new bonds to the point where it can eventually explode. And so sometimes you have to let a little bit of that gas go. That scared me. So did you learn the difference between a synthesis and a decomposition reaction? Hopefully.
All right, so in your group, take 1 minute and talk about the major differences between synthesis and decomp.
Combining atoms. So I guess with the general reaction, probably synthesis would be like A plus B to get C, and then decomposition would be C, and then you get A plus B.
All right, show me with your hands what synthesis does.
It
Comes together and decomp goes apart, right? So that's a pretty easy way to think of it. I have some like little diagrams and some general equations up here that can help you see that like through a real example. So this is your definition, right? This is your definition. This is your general formula. These are two very, very specific, like memorized styles of synthesis that we must know. I encourage you to be putting this in your foldable so kind of everything's in one place. So I'm going to be quiet, and then we'll use examples to illustrate what these really are. You should have enough space in your foldable to get all this in there. And if you're not a marker, writing with marker person, I get it. Use a pencil or pen. I just wanted to have a little color on there. So the general equation is just like you guys indicated, you make two things go into one. I did say it has one product most of the time. Remember, we're in like intro to chemistry, so I don't want to lie to you, but I have to kind of like limit information flow before your head explodes. So synthesis most of the time will make one product, sometimes it'll make two products, and we'll have a couple examples that we will actually experience today and throughout the rest of this unit. So to kind of make that like not the golden rule, okay? It's just a general rule. So we have our first type of synthesis, which is called binary. So we keep using that term binary. It simply just means what? Two elements, right? So two elements are involved. So I have one example where we have a metal and a non-metal. This non-metal is probably gaseous. Sorry, I don't know what's so solid there. Likely, it could be. We do have some non-metals like iodine. That forms the solid. So regardless, we have a metal and a non-metal. Well, we know what happens. We know when metals and non-metals come together, what kind of compounds do they form? Metals and non-metals. Oh my gosh, we've forgotten. Okay, metals are low in electronegativity. They're really willing to give up electrons. They have 1, 2, 3 valence electrons. Non-metals are really high in electronegativity. They have 6 or 7 electrons. They're like, please give me an electron. What's going to happen between a metal and a non-metal? What kind of? Ionic formation, right? So there's an electron that's transferred, and they're like, oh, I'm positive, you're negative, let's bond, right? So that's definitely an ionic bond that will form. So with that ionic bond, the ions will have charges, and those charges that we already know, we must crisscross charges in order to make this reaction look correct. So give me your favorite metal, Chandler. Favorite metal. Today, sir. Let's go. Okay, potassium. So we've got potassium, put K solid. And I need a non-metal. Anybody? Nitrogen. I like it. Okay, so let's add nitrogen. And so it's potassium plus nitrogen. Is this how I write nitrogen by itself? No, how do I write it? N2 and then gas. All right, so potassium is combining with nitrogen gas, diatomic, and to make what? What's the name when potassium and nitrogen come together? Potassium nitride. Okay, so we know potassium nitride. We're good with nomenclature. So potassium has a what charge when it forms an ion?
1+.
A 1+. Okay, that's because it's in group 1. Nitrogen's in group 5. What charge will it form?
3+.
3-. So what will it form when it comes together?
K3.
K3N. Okay. So this is why nomenclature is going to kick your butt if you don't have your crisscrossing of charges and everything with you yet, okay? So there's our potassium plus N2 makes potassium nitride. Now what must we do? Balance. So I've got 1 potassium, 3 potassium is what I need. A 3 over here, okay? And then I've got 2 nitrogens and 1. So what do I need? 2 where? In front of what? Potassium what? Nitride. You can't just say potassium because that's that one, okay? So if I put a 2 here to apply to the nitrogen to satisfy this guy, nitrogen's fine, right? So what do I have now here? 6 potassium, so I need a 6 over here. Okay, so that's a great example. Thank you guys, okay? Now moving on to the second style, you've got metal oxides, so that just means a metal bonded with oxygen and water, and that's going to make a metal hydroxide upon synthesis. So give me another metal, Manoff's table. Sodium, okay? Everybody, sodium oxide, give me the formula. Think first. Might need to look and think, oh, it's metal and non-metal, it's ionic. Na. 2. Oh, what's sodium's charge? 1+. What's oxygen's charge? 2-, crisscross, right? So again, nomenclature, right? So this is a metal oxide. We're going to add that to water. And if it helps you, I think it will. I don't always write water as H2O. I write it as HOH because it's still 2 H's and an O, so it's still correct. But you might be able to see how this exchange occurs. So sodium is a cation, right? It's a positive charge. It's currently bonded to this anion, this oxygen. So similar things are going to work out. Like the rule of positives and negatives attract is always true for us. So which of these is negative? The H plus or the hydroxide? It's negative, right? It's an OH negative. So sodium is going to be like, hey, let's get together, make sodium hydroxide. And then we're going to figure out what this other stuff's doing, but I think you'll see it in the end. So I have sodium and I have hydroxide. What are the charges on both of those? 1s, right? So that's going to make sodium, and I'll put parentheses so you can kind of see the hydroxide better. Okay, so what's really happening here is there's 2 sodiums, but there seems to be only 1 hydroxide here, right? But what happens when I put this O and H together? It makes 2 hydroxides, and so sodium's able to do that twice. So that's a lot of thinking that you're probably not going to do, but I just wanted to help explain the process if you needed it. But in the end, let's just balance, just like normal. How many sodiums do I have? 2, so what do I need here? 2. And with everything else, we're going to have to look at them separately. How many O's do I have? 2. How many O's do I have over here? 2, because that distributes. How many H's do I have? 1, 2, and then also 2. So it's balanced. 1 to 1 to 2 ratio. Okay, I'm giving you examples so that you're seeing how this works, because the general equations are worthless to us. We will be using real deals. So I would be writing this down in the future, okay? So these are some great illustrations. I'm giving you about 30 seconds if you choose to use those. Moving on to decomposition very soon.
Is the picture going on like the front?
The front, yep. Sorry, this was supposed to say like front. I don't think you have a whole lot of space on the inside after we get our examples in there and illustrate our definitions and so forth. So that should probably go on the front. Everything else goes on the inside. And absolutely, you can put more than one explanation or one example. And if you want to illustrate on the inside, kudos to you. I just wanted to give you a chance to leave yourself some space to work with. Okay, so I believe I printed this for you. Is this on your paper?
Yes.
Yes? Okay. I want you guys to go ahead and approach 1, 2, 3 using the rules we have just talked about. Repeat 1, 2, and 3. And I have printed it on your paper so you have room to write the reactants, yields of products. You cannot just write the products. You must write the reactants, yields of products. Take about 30 more seconds. You're okay. All right, come back to me. 3, 2, 1. Double check those diatomics, H2 plus Cl2, and then we made an acid. Acids are, they behave ionically, so that's an H plus, Cl minus, crisscross, no extra subscripts. What do I need here though? A 2 to balance everything out. Good. Magnesium is a singular metal. Notice that we don't always have the phases of matter like solid, liquid, gas. It's very helpful in some situations, but we're just working on predicting products here. So these two reactants react to make magnesium oxide. Why are there no subscripts here?
They're both 2 minus and 2 plus.
Okay, so we wrote the empirical formula, right? So we took a 2 plus and a 2 minus, crisscrossed them, reduced them. And then what do I need here? A 2 to satisfy this oxygen, and then a 2 here to satisfy the magnesium that I've just adjusted. Okay? And then barium oxide and water, BaO, why are there no subscripts here?
It's the same way as everybody's.
So 2s and 2s reduced down to 1s and 1s, good. Water, and if you want to write as H2O, totally fine. I just think this helps a little bit. What would this make, guys? Spell it out for me.
Parentheses, OH, 2.
Good. Barium is a 2 plus, hydroxide is a 1 minus, crisscross that over. How many bariums do I have across the board? 1. How many oxygens do I have across the board? 2, 1, 2. So that's why we can't call this out as hydroxide all the time, because I do have 2 oxygens in separate areas, but this overall makes 2 oxygens. And how many hydrogens do I have? 2 and 2. Check. 1's across the board. All right, so I'm going to hold off on this one for a moment because I'm going to do a demonstration for that. Before we do our demonstrations, we're going to do decomposition, and then we'll go to the fume hood. Okay? This is the fun part. Hold on. I'll come back and do a couple more of those. I'm not trying to kill you with examples, but there are a lot of different ways that these can occur. So same story, but there are 4 decomp types that we must know. Okay, I'll give you some tips on memorizing those shortly, but I'm going to let you write down these first. Here, and it's a decomposition style. So it just helps a little bit to color code. If you need more room, you've always got to hold back in your foldable to add more detail. So don't feel like I'm trying to squish your notes down. All right, let's walk through a couple of these together. If you're still writing, just kind of wait till we get to that part so you can listen and write down examples as well. I would encourage you to write these examples down either in your foldable or in the back or in your notes someplace, okay? So not optional examples, get these down. So we have 4 styles of decomposition, but the common thing for all of them is they start with what? Well, that is a common theme. They do start with metals, but they all start with they all start with how many reactants? 1, and that is going to be true for everything. 1 reactant gets broken into many pieces. Sometimes it's 2 products, and actually sometimes it's 3 products. So you can see in this example, I've provided 2 products as an example, but it could be 3 products, it could be 4 products. Sometimes we'll see in our labs that we actually deal with more than just 2 products being produced. So binary again means 2 types of elements. So if we have a singular ionic compound, metal, nonmetal, and it breaks down, we're going to break it down into the metal component and the nonmetal component. So let's do copper 2 oxide. Copper 2 oxide. Ready when you are. Formula? Cu what? CuO, good, because copper 2, and then O is a 2, crisscross, nothing. So we have copper 2 oxide breaking down, and you'll notice that I put a big triangle here, because I'm saying it requires energy. What do you think I'm trying to indicate to you? Done? Put a triangle over here, because a lot of times these don't just poof and happen in no time. You have to heat them up, and then they'll start to decompose. So big triangle is going to help you understand that that's requiring heat. Okay, so what's the metal it's going to break down to? Everybody, come on. Copper, right? Is there anything weird about this? It's just copper, right? We're not going to try to make it a 2+ because we're not poofing into ions, so no ions over here, meaning no charges are going to apply. All right, what's the nonmetal we're breaking into? YO2. It's by itself, therefore we write it diatomically. Very good. All right, to balance it, what do I need? 2 in front of the copper 2 oxide and 2 in front of copper. Good. Okay. Next we have metal carbonates, and so we actually know what carbonate is. It's CO3 charge. CO3 2 minus. Okay. So if I have a metal carbonate, let's say we have iron 3 carbonate. Iron 3 carbonate. Formula. Fe2 CO3 3. Okay, so it's iron 3 carbonate, and that 2 is from carbonate. All right, we're going to decompose that into what's the metal oxide that this would form. So who's the metal? Iron with a charge of what? 3, because I had to tell you this was iron 3 carbonate, okay? That's the 3. All right, so then I'm making iron 3 oxide. What's the formula? Fe2O3. Good. So that's rust. Iron 3 oxide is rust. All right, so iron 3 carbonate breaks into a metal oxide, iron 3 oxide, and what gas? Also known as carbon dioxide, right? All right, so here's the deal on this one. Carbonates and chlorates, kind of people mix up because they look kind of similar. Carbonates have what element in them? Carbon, right? So carbonates make carbon dioxide. Carbonates make carbon dioxide as the gas. Because we're heating this thing up. A lot of times we're going to be making gases. You'll see that's also a common theme, gas. But chlorates, one would think, oh, I'm going to make chlorine gas. But chlorine gas would kill us all because it's toxic. So if we're doing labs with these, I am not going to make a hazardous gas like that. So choose the friendlier gas of oxygen. It's much more friendly than chlorine gas. Because we deal with carbon dioxide every day. Where's that? We breathing it out, right? We also deal with oxygen every day. We breathe it in. So think of things that are familiar to you that are common in our world. Okay, so carbonates make carbon dioxide. Let's balance this. What do I need? What's not balanced right now? So the ions are balanced, yes? Okay, how about the carbons? The carbons are not balanced, right? How many carbons do I have here? 3, so what do I need here? A 3. Okay, that 3 applies to carbon and oxygen. How many oxygens do I have here? 6, and these? 9. So that's an additive summation step because I'm having these added to these. So that's 6 plus 3 is 9. How many oxygens do I have over here? 9. Yay, it balanced itself out. Okay. And metal hydroxides, what do you notice about this one? This should look very familiar. No, not the fact that it's water. What's familiar about this reaction? It's like the synthesis, but the opposite. It's completely opposite. So if you already memorized your syntheses, you already have half the decomps figured out because the synthesis was metal oxide and water makes metal hydroxide. And the other synthesis was a metal and a non-metal make an ionic compound. So this one and this one, I would indicate on my paper someplace, these are opposite of the synthesis. So you're just memorizing 2 of these, not 4, okay? All right, so metal hydroxide, we'll get back, we'll do an example of that one shortly. Metal chlorates, let's do potassium chlorate. What's potassium chlorate? Okay. ClO3. And that's a 1 plus and a 1 minus, so therefore we're good to go. And we're going to break that down into metal chloride. Well, who's the metal here? Potassium. So I'm going to make metal or potassium chloride. So what is that? Okay. Right, they're both 1s and 1s. So that's KCl. And then what friendly gas? Oxygen. Okay. So right now it looks like we've lost an oxygen. That's just because we simply haven't done what? Balanced it. So how many potassiums do I have? 1 and 1. How many chlorines do I have? 1 and 1, or 1 and 1. How many oxygens do I have? 3 and 2. What do I think of now?
LCM.
LCM, right, at least common multiples. So therefore I need to think up to what? 6. So I need to get 6 oxygens on the table, right? So how do I do that here? Put a 3, so that's going to make 6 oxygens. How do I do that here? In front of the whole shebang, right? I can't put it in the middle anywhere because that's not a coefficient. So now I've got 6 oxygens, but I also have what? 2 potassiums and 2 chlorines. So if I put a 2 here, that satisfies everything. Okay? All right, so this is a nice image. If you wish to draw it, I also have some others down here. I'm going to give you a second if you need it. All right, and you have 1, 2 examples to do right now. We'll do 2 more in a second. And these, I believe, are on your printed lecture notes again. I gave you yesterday.
Yeah, it's just
If you didn't get the picture, it's on your own time. You need to do these right now. That's the least important thing to do right now. You need to be working on the 2 examples I've asked of you. If you see on your paper there are 5 examples, go ahead and do the last 2 because those are the last 2 I'm going to have you guys work. So follow the rules you just wrote down because that's the only way you're going to get these right for now. Eventually you'll have it in your head. Come back to me on the first two. If you need more time on the second two, we'll get there. All right, so we have to think about this in a very, very simplistic manner. First of all, do you identify this as decomposition reaction? Yes or no? Do you identify this as a decomp reaction? Yes. What's the reason? One reactant. If you see one reactant, there's nothing it can do with itself. It must break down. So it must decompose. So first of all, classify as decomp. Then you're like, okay, I've got 4 types of decomps. Binary, metal carbonate, metal hydroxide, and metal chlorate. Which of these is it? Metal carbonate. Okay, so you have to think about, okay, how do metal carbonates decompose? They make what and what? Metal oxides and carbon dioxide, right? So carbonates make carbon dioxide. Carbonates make carbon dioxide. So I already know carbon dioxide. I can write that off the cuff. That's nothing. It doesn't matter if I write it first or second, by the way. So carbon dioxide is definitely one of the products. And then metal oxide is the other. Well, who's the metal? So I'm making sodium oxide, which is what? Not NaO. Na2O. You've got to crisscross charges, right? This is a covalent compound. We wrote it like it should be written. If it's ionic, you must crisscross charges every single time, okay? So add those together and you have your 2 products. Metal carbonates make metal oxides and carbon dioxide. Balance this baby out. What do we need?
Sodium.
I already have 2 sodiums. It's balanced, thank you. It's naturally balanced in this case because there's 3 oxygens on both sides once you add them up. All right, water, you recognize it as decomp because what? One reactant again. You recognize it as which of the 4 types? This would be binary. Now, no, Ed, I know it's not a metal and a non-metal, but it's simply binary. It's just H's and O's together. It's not a metal hydroxide by any means because there's no metal here. So, break it up. What's it going to make? H2 and O2. To its 2 elements, right? H's and O's made it up. It breaks into its 2 elements, but we can't write H and O because those are singular, and the diatomics are these are those diatomics. What do I need here? A 2, and what do I need here? 2. And what do I need here? A 1. Okay. All right, so let's work on the next 2. Magnesium chloride, what do you recognize that as in terms of the decomps, the 4 types? That's not a chlorate, that's a chloride. It's just binary, right? Break it into what?
2 elements.
2 elements, which are who?
Magnesium.
Magnesium and like this?
Cl2.
Cl2. Now, I know it looks like we just pulled those babies apart. I know that's what it looks like, but it's legitimately not what's happening. We make 2 different products, 2 different elements, and that's just natural for magnesium to be singular and diatomic chlorine to look like this. So we didn't just cut it in half and call it a day. And it's balanced, of course. Calcium hydroxide, which are the 4 types? Metal hydroxides, and they break down to what and what? Metal oxides and water, which is the opposite of the synthesis version of that. So metal oxide will be who here? So why is it CaO and not any subscripts?
Because
They reduce. Yeah, so they 2s and 2s crisscross reduce to 1s. And what? H2O, if you want to write HOH, it's fine. Who's not balanced? Say again? It is balanced, right? So there's one calcium, 2 oxygens, and 2 hydroxides across if you look at it. Woo! Meet me at the fume hood. more space on this side if you guys did. Did you guys notice there's a lot more space right here? Short people in the front, that kind of thing. All right, so what I have for you is my decomposition reaction, and in this test tube, this is potassium chlorate. What's the formula for potassium chlorate? Potassium chlorate. One more time. Okay, let's make a consensus here. K. All right, still didn't get it. Can you guys talk real fast? Potassium chlorate. No, that's chloride. All right, and no, what's chlorate's charge? And what's potassium's charge? So therefore, this is KCl. O3. Oh my God. Okay. I know, but the whole class wasn't. I was trying to get the sorry. You got to stand up, lady. There you go. Show them. Okay. So basically, I'm making molten. Does anybody know what molten means? Molten potassium chloride. Chlorate. It means I've melted it. Okay, so I've almost officially melted potassium chlorate. This is not the demonstration. This is just me prepping the demonstration. So you can see it's starting to decompose. It barely. You see these little couple bubbles. And those bubbles are just kind of going to hang, and I'm going to show you how potassium chloride reacts with sugar. It's not potassium chloride anymore, it's decomposed. Ooh. Courtney, it's so cool. So, I'm going to turn that unit on. So, basically it's going to smell like s'mores. I'm sorry, guys. Okay. So, essentially, potassium chlorate is a chlorate. What does it break down to? Metal chlorates break down to?
It's KCl.
KCl and?
And then it's O.
No, friendly gas.
O.
Friendly gas? O2. Okay, so oxygen, O2 is very, very, very reactive. I gave it some sucrose. I gave it some glucose, right? Your body takes in glucose. Your body takes an oxygen. What does it do? What's that process called in the mitochondria? Makes ATP. The actual cellular respiration. But what type of cellular respiration requires oxygen? No, you don't photosynthesize. No, wait. That's just cellular respiration. But is it the one that requires air? Is it non-air or the air one? Aerobic. Okay, so aerobic respiration. Okay, so this thing basically did aerobic respiration in a test tube. I fed it some glucose and it goes, ooh, reacts with the oxygen, makes fire. Right? So basically it did that, but that's what your body's doing, but you don't make fire. You make 36 ATP. Okay? So, but that's what you smell it? S'mores. Okay, so that's a decomposition reaction, but we took advantage of the decomp by that oxygen, and I fed it glucose, and it made fire. That, of course, was combustion, which is what we're talking more about tomorrow. Okay. So, I have two more. I have to do this one in the do you smell the s'mores? It's not hazardous whatsoever. It's just dang it. Well, I'm running something more now. So, is there a scapula here? Oh, yeah, so it's okay, so I'm going to put a little bit of, I'm not going to do this out the fume hood because it makes bad gas. So, we put a little bit of zinc. This is like metal zinc. It's legit zinc. Okay? We're going to add some iodine. How does iodine, what's its formula? I2. So what am I adding together? Or what am I doing? Zinc and I2. What am I doing? What type of reaction? Binary synthesis, right? So what's it going to make? Give me the full thing, people. Zn plus I2 makes what? Can you give me the name and then we'll talk about it? Zinc iodide. And zinc iodide would be a synthesis reaction because I'm simply adding two things together to make one compound. Assuming I get a little bit of iodine. So not right when they touch each other. So that's the thing. Sometimes synthesis is cool and it will do that. It's supposed to make the same compound. Maybe get on the iodine. I'm just going to see that in a second. Okay? And at this point, I'm going to put this back in the fume hood because it makes nasty gas. And we're going to I'm going to drop a water on there so you can see the reaction. I hope it works. Sometimes it doesn't. I'm not magical. It's got science got to work, right? So, and that's it. That's what it does when it makes zinc iodide. It makes a purple poop. Let's see if I have a little more. It looks like a genie on the bottle. So basically that's it. I didn't put that zinc in there to make a big poop because it's purple, but it does that. So in that little pool of water, there is zinc iodide. Okay? I have one more. Okay. Hold on. Promise this is going to be worth your time. Alright, this one you need goggles on for. Turn around. There you go. Alright, and then back it up. We'll give it a little bit of space. A little bit of space. So this is technically synthesis because I'm making something, but it's one of the syntheses that makes two products, not one. So who's ever heard of what alkali metals do in water? Okay, they explode. If I was a teeny tiny bit, hopefully they're not going to explode. They're just going to make a little, like just a little mini tiny explosion. So my goal is for you to give me some space. Back up. Don't touch the left station. Back up. Okay. And I have a little piece of potassium because my chemistry teacher had a chunk this big, and he was like, "Oh, when we were really good, he would do this demo." So I mean, this is a treat. And we would beg him to do it, and he's like, "I just can't do it." I'm like, "Fine." So I loved it. So these are big chunks. Ooh, these are big chunks. So this is stored in oil because potassium is an alkali metal and it's very, very reactive with air and water vapor in the air. And there's some water. You guys see that water? Yeah? Okay. So this is what potassium metal looks like. It's covered in oil right now. So I'm just gonna set. Don't touch my stuff. This is stored in kitty litter because it's flammable. We're gonna see what happens. So, I should put this in the June head now. Oh no, I spilled on my face. Back up, guys. Back up. Back up. You got the mommy to walk off right now. Sometimes it's off. Want to leave a little burn mark? No, just me. Okay. That happens sometimes. Last time I hit the ceiling, which wasn't a big deal. I look like I'm fine, right? Yeah. The red spot? Okay. Ooh. Just a little, no, I mean, it just scared me more than anything, but because I knew that could happen. And it's smoky in here, so you guys go back to your seats, and I'll tell you what's next for you. You really just have a couple more examples to do before we leave. So we've already 10. I'll tell you guys what to do. Turn to the back. Turn to the back of your lecture sheet. I should have put that down. Woo. Yeah, but if it's not safe, that's cool. But the purple potassium is making purple color because that's what it does with when you excite electrons, when it makes fireworks, it makes purple, etc. Okay? So, you guys have this, yes? It's on the back. You guys are doing synthesis, so those 5, and then the decomp 5. So that's what this is specifically for homework. So get started now. I'll turn on announcements shortly. And then I want you to begin PS11. There's not a whole lot you can do yet, but there definitely is some you can do with PS11, okay? So start those in your groups now. Synthesis 5. Yeah, synthesis 5 and decomp 5.